Hi, and welcome to today's episode. After seeing an agent learn, you might wonder how computers become artificially intelligent without learning. Today, we want to take a closer look at the difference between traditional or symbolic AI and machine learning, which we learned about in the last two videos. As we have already learned, machine learning is a part of AI, but not all approaches in AI use machine learning. A lot of these other approaches fall under the category of so-called symbolic AI. This is, historically, the first approach to AI. It is based on the symbolic representation of knowledge and uses logic and reasoning to find a solution. Symbols are just a fancy way of saying we can use electric signals to represent anything from the real world in a computer system that the computer can work with using logic. The machine that defeated Kasparov in chess, Deep Blue, was indeed a purely traditional AI in this sense, while the system that defeated the world-famous Go player used machine learning and some traditional AI methods as well. To illustrate how different these approaches are, we take a second look at our mini chess game from day 2.
Yesterday, the crocodile player had a list of possible states and actions, where suites helped him decide which action to choose. In the beginning, we had all the suites for all the moves. Over time, the distribution of the suites changed, so that now the monkeys are not able to win anymore. So the agent learned which moves led to success and which ones end in defeat. To explore what a symbolic AI might do, let's keep the game set up as it is and just swap the list of possible moves for another list. So we don't need all of those chocolate tokens anymore. We can see this is the computer's knowledge base. Expert systems like this are a popular form of symbolic AI. They use a set of defined rules, like the if-then statements here on the sheet of paper. Let's now play one round of mini chess again. I'll just move this piece over here. Oh. The crocodile player, in this case Tillman, checks his knowledge base in form of the rules on the paper and selects the then part of the fitting rule. Now I'll try to win by capturing his piece here. But as he has already a set of pre-calculated rules that tell him how to react, he's not so dumb as to capture my figure, but he's just blocking me and therefore winning the game. Let's reset the game and try a different move. I'll move this piece over here. Once more, the appropriate move of the knowledge base is telling the computer to capture my piece. Let's try our sneak through the middle. The computer is not trying to capture me in this moment now, but is once more just winning the game by going to the end. Whatever I do not have any chance to win. So the traditional AI needed to do a lot of pre-calculations of the states, searching for the best possible moves. It uses some kind of logic to do that, essentially calculating and evaluating everything in advance. With the machine learning approach, we had a self-learning agent that need to be trained and use data to get better over time. With knowledge of the rules, it tried and failed and got better over time by gathering experience.
Deep Blue behaves more or less like the chess version we just played. To master chess, it evaluated up to 200 million positions per second, essentially pre-calculating as many positions as possible to see if a move will eventually end in a victory. In contrast, the system that beat the Go champion was trained with 30 million captured moves and also games against itself, trying to maximize its reward. Why was Deep Blue not able to compete in Go? Let's have a look on how hard it can be to pre-calculate all the possible board positions. Let's compare the complexity of our mini chess with chess and Go. The board size of a mini chess is only 3 by 3, limiting our number of possible actions per turn to an average of 4. With a maximum of only 3 rounds in length, we have less than 100 possible different board positions. This makes it rather easy to evaluate all possible board positions and see if a move will eventually end in a victory. If you look at chess, we have a board size of 8 by 8, increasing the possible actions as well as the game length by a lot. We already have 10 by the power of 44 possible game states, making it a lot harder to pre-calculate and evaluate all of those states. Go is even more complex. We now have a board size of 19 by 19 and overall about 10 by the power of 177 possible board positions. That's actually bigger than the estimated number of atoms in the universe. If we compare the opening moves in chess and Go, we have 35 possible board positions in chess and already 200 in Go after just one turn. With the next turn, we already have around 200 times 200 possible board positions in Go, and that with a game length of up to 200 turns. We call this phenomenon a combinatorial explosion. The huge amount of board positions makes it impossible to pre-calculate and evaluate all those states. That's why AlphaGo used machine learning.
While we cannot fit the entire universe or the entire knowledge of the universe into a computer because it's just too much information, we can still feed a lot of information or knowledge into a machine, for example, to discover side effects of medication. As we know, with symbolic AI, we need to represent knowledge and problems using symbols and then use logic to search for solutions. The basis for this kind of knowledge representation are symbols, as the word symbolic AI suggests. A symbol might be the state of the chessboard, a person, a number, or a drug. A drug might contain an active substance. This relation, in this case contains, describes how symbols, in this case only 2, but it can be more than that, interact with each other. Sometimes, when we're really sick, we need to take more than one type of medicine. In this case, we need to know which of them we can take together without risk. This knowledge can be also explicitly represented in the computer. If the active substance leaf and mushroom are taken together at the same time, this leads to sickness. An AI system working with symbols can use logic to find out which drugs do not fit together based on its rule system. Using logic, it can therefore deduce that superhero pills and amazing medicine should not be taken together. By solving the rules from its knowledge base, the computer can even increase its knowledge base without the need for a human to define all possible rules. It can infer the rule that superhero pills and amazing medicine taken at the same time lead to sickness as well. In the same way, we can ask the system questions like, which drugs contains mushroom. The system will then look for matches in its knowledge base and returns them. In this case, the AI system will return all drugs that contain mushrooms, such as the superhero pill. Of course, we're not limited to this simple set of symbols and rules. Over the years, such systems have been built for medicine, for shops, for banks, insurances, and so on. They are called expert systems as they are supposed to place a human expert. So we've seen those AI systems use logic and reasoning. Another kind of similar technique they are using is search algorithms. Those algorithms search for the best next move in tic-tac-toe, or planning a route for a vacuum cleaner robot, or our spaceship that we used to follow along our AI journey. Even though search is today often not considered AI anymore. Remember the definition from the beginning? AI is the study of how to make computers do things at which humans are better at the moment. It still remains an excellent way to solve a couple of problems. The essential part is to get the knowledge into form so that the computer can use logic to process it and to generate a route. This might happen through cameras or sensors, like in your vacuum cleaner robot, or it's possibly predefined. Then, the agent can plan ahead what best to do to achieve its goal, for example, reaching a planet or navigate to a specific room. There are several steps involved to get to the final destination on the shortest path. If I am at the green planet in the top left and want to reach the little moon of the orange planet, I first need to fly to the planet down, below, and so on. This shortest way is something that search algorithms can find. When trying to solve reward search problems, those algorithms are facing giant search spaces. So the search algorithms need a lot of time to find the best solutions. If you've heard of it, they are often NP-hard or worse. So smart people invented algorithms that don't perform an exhaustive search of all the possible options. Instead, the paths most unlikely to lead to a possible solution are left unexplored for as long as possible. We've seen that those symbolic or traditional AI approaches are useful in a lot of situations. Symbols are used when the input is definite and falls under certainty. In comparison to a lot of machine learning approaches, symbolic AI can explain which rules have led to the solution. But when there is uncertainty involved, or when we need to describe how a cat picture looks in a way so that we can store it in symbols in a computer, or how to play Go successfully, it's just too difficult. This is one of the reasons a lot of attention regarding AI is actually about statistical approaches, mainly machine learning, as there is a lot of uncertainty in the real world. So for the next week, we'll take a closer look at how machines can handle the uncertainty of the real world by learning from data. Thank you guys for watching, and see you all next week.